This video is about basis vectors and coordinate systems. Finding a basis for a subspace is very useful because it describes the entire subspace using as small a set of vectors as possible. Using this small set of vectors, we can then define a coordinate system on the subspace in order to reach any point on that subspace. So first, let's start with the definition of what a basis is. A basis for a subspace H of Rn is a linearly independent set in H that spans H. So let's see what this looks like in two dimensions. For example, suppose that we have two vectors, v1 and v2. Now the subspace that they span is going to be this line in R2, which is the span of v1 and v2. Suppose also that we have just v1 by itself, and it also spans the same exact subspace if v1 is the same as it was over here. So in this case, the subspace H is going to be the span of just v1. From our definition of what a basis is, we can see that v1 is a basis for H, while the set v1 and v2 is not a basis, because it's not composed of linearly independent vectors. It has two linearly dependent vectors, and we want a basis to be the smallest possible set of vectors that fully describes the subspace. And in this case, since it's a one-dimensional subspace, that is just a line in R2, it's fully described by just one vector. In this case, we choose v1, and therefore it forms a basis. In any space Rn, there is such thing as a standard basis. A standard basis is just the columns of the identity matrix I, and it fully describes any space. So once again, looking in 2D, we can see that the columns of I are 1, 0 and 0, 1. So we can describe any vector in R2 by using a linear combination of these two vectors. So this forms the standard basis. We'll call it B1, and it's going to be made up of these two vectors, 1, 0 and 0, 1. And this is the usual coordinate system that we're used to. We usually define everything in terms of 1, 0 and 0, 1 and linear combinations of them. Now suppose that we have another basis for R2. And we're going to choose the vectors 2, 1 and 1, negative 3. So these are also two linearly independent vectors that span H, H being R2 itself, and therefore this defines another basis made up of these two linearly independent vectors. Now we can define any point in R2 by using a linear combination of these two vectors. And we can define any point in R2 in general with either one of these two bases. So for example, suppose that we are trying to get a vector that is 3, negative 2. This will be our vector x. So by using B1, our standard basis, we can see that this point, this vector, is defined by 3 times 1, 0 plus -2 times 0, 1. In other words, we travel 3 times along this direction and then 2 down over here, and we get to this point. So the weights of this linear combination, let's call them C1 and C2, are going to be 3 and -2. And therefore, we can describe this vector x as being 3, -2 in terms of the standard basis, which is exactly what we had before. We can also describe it, though, in terms of our second basis. We can see that this point is going to be 1 times the first vector, 2, 1, plus 1 times the second. In other words, it's going to go up to here and then down to there. 1 times the first plus 1 times the second. So the weights in this case are going to be 1 and 1, which means that the vector x can actually be described as the coordinate 1, 1 in terms of this other basis. So we have two different representations of the vector x in terms of two different basis sets of vectors. In general, we can create a definition for a vector x in terms of a different basis by using the following description. Suppose the set B, made up of the vectors b1 through bp, is a basis for a subspace H. For each x in the subspace, the coordinates of x relative to the basis B are the weights C1 through Cp, such that the linear combination C1, B1, and so on until Cp, Bp, which is equal to x, and the vector in Rp, so specifically this vector, which is now a p-dimensional vector, is called the coordinate vector of x relative to B. So in other words, we can make up x, which is an H, out of a linear combination of the basis vectors weighted by the weights C1 through Cp, and we define a new coordinate relative to this new basis as those weights. So in this case, we're in R2, and the subspace that we're looking at is also R2. Therefore, our coordinate vectors are both going to be in R2. However, if the subspace actually describes a lower dimensional space, then this would be different. So for example, going back to what we had before, we're still looking in R2, but now we're looking once again at some vector v, and suppose that this is going to be 1, 2. So this is our vector. So this spans a line. You can see that the subspace is defined as the span of this vector 1, 2. And therefore, we have a basis for this subspace, which is going to be just the set composed of this one vector, because any point on this line can be reached with a linear combination of this vector. So suppose that we want to then describe a point right here, which is this vector over here, which is -2, -4. So this vector, let's call it x, which is equal to -2, -4 in R2, can actually be described relative to our basis as just -2, since it's equal to -2 times the basis vector 1, 2. And this, of course, is in R1. So we can see that the coordinate relative to the basis can be in a lower dimension than the dimension that the subspace is actually in. So now let's look at how to find a basis for the important subspaces that we've seen before, specifically for the null space and for the column space of a matrix. So suppose that we have a matrix A defined by this, and we're trying to find all of the x's which solve the homogeneous equation, which defines the null space. So we're going to row reduce the matrix A augmented with the 0 vector, and this reduces to this, which leads to the following equations, and this leads to the parametric vector form solution given by this x. Let's call these three vectors here v1, v2, and v3. This solution for x gives us the span of the entire null space weighted by the free variables x2, x4, and x5, and is a linear combination of these vectors v1, v2, and v3. These vectors are linearly independent by construction and therefore form a basis for the null space of A. So we see that B for the null space of A is equal to the set of these three vectors v1, v2, and v3. So from this we can see that even though x, any given x, has to be in R5 because there are 5 entries to it, the x in terms of the coordinates that we just defined, in terms of this basis for null A, is going to be in R3 because we can traverse the entire space by a linear combination of just 3 vectors. So as an example, suppose that we want to look at x is equal to 7, 1, negative 6, 2, negative 1. We can actually find that this is going to be 1 times v1 plus 2 times v2 minus 1 times v3. And therefore, relative to the basis formed by looking at the null space, we get that this coordinate is 3-dimensional and is 1, 2, negative 1. And that describes the exact same point. Since we only need 3 coordinates, 3 weights, in order to get to any point in this entire subspace, since we're spanning a 3-dimensional subspace in R5. In order to find the general b coordinates of a vector v, you have to solve the system bx equals v, where b is composed of the basis vectors you want to use. This will solve for an x which comprises the weights necessary to reach v as a linear combination of the vectors in B. You are guaranteed to have a unique solution since the vectors in B are linearly independent and span the subspace, both from the definition of a basis. Now let's see how to find a basis for the column space. To find a basis for the column space, we're going to look at the reduced form of a matrix A. So this is our matrix from before, and it reduces to this just like before, and let's call this matrix D. We can denote the columns of these matrices by letters, and that'll help us in a little bit. So let's say that the columns of A are A1 through A5, and the columns of D are D1 through D5. Now we can see in D the linear dependence relations between the columns very easily, because in the reduced form we have columns in the form of 1, 0, 0, 0, 1, 0, and so on. Therefore, we can see that D2 is going to be equal to negative 2 times D1, because it's simply negative 2, 0, 0, and D1 is 1, 0, 0. Likewise, we can see that D4 is going to be equal to, since it has a negative 1 in the first place, it'll be negative d1 plus, with a 2 in the second spot, it'll be 2 times d3. And d5 is going to be 3 times d1 minus 2 times d3. So from this, we can see that since d2, d4, and d5 are just linear combinations of d1 and d3, then the column space of B is going to be just the span of d1 and d3, since they make up every other column anyway. And therefore, a basis for the column space of D is going to be the vectors d1 and d3. Now this is for the column space of D. When we perform row operations on the matrix A, we actually change its column space. Therefore, the vectors that span the column space of D do not necessarily span the vector space, the column space of A. We can easily see that, in fact, here, because linear combinations of d1 and d3, they'll all have zeros in the last entry. But A has non-zero entries in the third row, and therefore we can't possibly span that entire space by using linear combinations of d1 and d3. However, this still tells us something useful. Row operations to reduce from A to D do not change the solution set of a system of equations, and the dependence relations are determined completely by the homogeneous equation, and therefore the solution set does not change. This means that the linear dependence relations in A should be the same as in D. So let's check that. Based on this, we should have the exact same linear relations. A2 should be equal to negative 2a1, because d2 was equal to negative 2d1. So let's check that. Negative 2 times negative 3, 1, 2 is equal to 6, negative 2, negative 4. Good. A4 should be equal to negative a1 plus 2a3. So we have negative minus 3, 1, 2 plus 2 times negative 1, 2, 5, which is equal to 3 minus 2, negative 1 plus 4, and negative 2 plus 10, which is 1, 3, 8. And that is exactly A4. And finally, A5 should be 3A1 minus 2A3. So 3 times negative 3, 1, 2 minus 2 times negative 1, 2, 5. And that is negative 9 plus 2, 3 minus 4, and 6 minus 10, which gives us negative 7, negative 1, negative 4. And that is also correct. So we can see, once again, that the linear dependence relations between the columns of A are the same as those between the columns of D. And that's all we have to know, because now we can see that the column space of A is going to be spanned by columns A1 and A3. And therefore, a basis for the column space of A is going to be A1 and A3. So the important part in here is to see that the linear dependence relations are the same, but the vectors themselves are not. Therefore, what we've seen is that if we can span the column space of D with a given set of its vectors, we can span the column space of A with the same set of vectors corresponding to the columns of A. If we span with D1 and D3 for D, we span with A1 and A3 for A. So in other words, we can span the column space of A and form a basis for it by using the pivot columns of A. The pivot columns are defined by the columns which have a pivot in them once we reduce it to its reduced form. So again, importantly, to span the column space of A and to form a basis for it, we have to use the columns of A itself, not of its reduced form, but we use the pivot columns, which are the columns with a pivot in them after reduction. And to conclude this, we can see that if we look at a point x or a vector x with respect to our new basis for the column space of A, this is going to be in R2, since we can span everything with just two vectors, and so we can move around in this space by a linear combination of A1 and A3, even though the column space of A is actually a three-dimensional space. Overall, we have seen what a basis is and how to define coordinates in terms of that basis. This can greatly simplify a subspace, since a subspace spanned by just a few vectors in a high-dimensional space can be fully characterized by much fewer coordinates. We have also seen how to find a basis for two very important subspaces in linear algebra, the null space and the column space.